So in this video, let's read the datasheet. This DC-DC controller from Analog Devices is MAX3864 to 38643. It's a very small part, and 1.8 volts to 5.5 volts input range, and very low quiescent current, and 300 nanoamps, and the output current about 700 milliamp. Okay. This is a whole family parts. They all have very same 1.8 to 5.5 volts input range. The output current depends on the part. Could be 1.75 milliamp, 350 milliamp, all the way up to 700 milliamp. The peak efficiency, remember, is peak efficiency can up to 96%. Okay, the application is not very interesting. Let's look for the benefits and features. Because it's very low quiescent current, so it's good for the battery life. The shutdown current when the part is disabled or the current draws 5 nanoamp. The peak efficiency is about 96%, and when you go low output current, the efficiency could be lower at 80%, still reasonably good, and very easy to use. So it's based on the parts. A options, you have B options. A options adjustable. You can use a feedback resistor to adjust the output, and the B options have an internal feedback resistor, so these have a fixed output. And also some other features include they have reverse current blocking shutdowns. That means when the part is shut down or disabled, no current can flow back into the source. And some parts have optional active discharging feature. That could be important for certain applications. So that means when the part is disabled, it can actively discharge your output capacitor. The typical operating circuitry is very simple. So we have the DC-DC controller here. You have your inductor as an energy storage device, and the input capacitor, and the output capacitor, a resistor to set the feedback for the set of output value, and the enable or disable pin if you want. Okay, keep going to in the datasheet. We've just quickly go through this, some electrical characteristics. We for input 3.3 volts, output 1.8 volts, and the input capacitor 10 microfarad, and the output 22 microfarad. And the shutdown current, we know the disable current, so it's up to 5 nanoamps current. And input range, we talk about this, 1.8 to 5.5. That's under voltage lockout. That means if your input voltage is too low, you cannot enable the parts. So that depends on the feedback resistor, could be 1.75 volts or 2.6 volts. Output range is very wide. It's from 0.5 to 5. Accuracy is reasonably good. And the DC line regulation, that's the how the output voltage change with the output current. Okay, when the output current change from 10 milliamp to 160 milliamp, if your output is 1.8 volts, how much this output voltage can change? It's up to 1.5%. Okay. Inductor peak current, depends on your parts. This one's have a 700 milliamp output current, so the inductor peak current could be up to 1 amp to 1. The max could be 1.2 amps. So when the part output current capability is lower, so the peak inductor peak current is also lowers. So this is kind of important when you choose the proper inductor. So these parts include two transistor or two MOSFETs. One's high side, one's the low side. We will talk about that later. Basically, when this MOSFET is turned on, they have a certain on resistance that can up to from 320 milliohms all the way to 95 milliohms for the PFET, and for the NFET could be from 50 milliohm to 150 milliohm. This is important because all the current passes this all resistance will generate heat. That's basically where the major heat comes from when the parts is running. Okay, here's some diagram. We can just go through some of them. Most of just the takeaway is most values we specify in the data sheet and depend on the temperature. For example, the shutdown current. The shutdown current is when room temperature 0 to 25 degrees, very low, like a couple nanoamps. One is 75 degrees, all the way go to 25 nanoamps. Okay, it all has some certain temperature dependency. You do the total system current, the quiescent current, room temperature 300 nanoamps, and then 75 could go up to 400 nanoamp. So here's the importance is efficiency curve. For example, here, efficiency out is 3.3 volts, and if we have a V in 5 volts, that's this curve here. And the efficiency, that's how efficient you can convert input energy to the output energy. So the efficiency is highly dependent on the current. When you have a higher current, like 10 milliamps here, it's about 90%, 90 to 93%. If it's 100 milliamps, could be up to 95%. But when you go below 10 microamp, will be the efficiency will be much lower. So that's basically lower current, lower load current. You have a very low, relatively lower efficiency, and higher current have a higher efficiency. Remember, this is in all the here is in log scale, so so the range is very wide. It's very similar curves for the different output. We can skip that. Okay, this is load regulation relative to the low current, for example. So the regulation, if we have an output 3.3 volts and say input 5 volts, that's this curve here. Okay, and when your load current is relatively low, say up to a milliamps here, the output is very the output is about 1%. This is in percentage, so the output of 1% was 3.3 volts. And if your current is very high, your output will be minus 1%, so it will be lower than 3.3 volts. Okay, and here's a typical startup sequence. So what you have here, that's the input voltage. This is a steady voltage on the input side. So you have an enable signal coming, because this comes from a digital signal, have a very fast change, sharp rising edge here. And after a certain delay, let's see, roughly 500 microseconds per division. So roughly 500 microseconds later, the DC-DC converter, the controller start working, and your output slowly ramp up to your output voltage. So in shutdowns, similar sequence shutdown. When you shut down and the enable signals goes low, here your the DC-DC switchers stop running right away, but because the output capacitors and your output voltage will slowly go down. So this is a pin configuration. It's very small parts and only 6 pins, so it's very easy to use. Although the pitch from here to here is very close, but in the layout you can easily fan out from this way, this way, this way. So basically you don't need to put any vias or anywhere in the part, so it's not a problem. 6 parts, we have an input, a switching node, that's the node you connect the inductor to. We have ground. We have a select, R select, the resistor to set the output, or no connection if it's fixed output and output value and the enable pin. Here is an interesting part. It's a functional diagram of these parts, and just like a quick reminder of what is the topology for DC-DC converters. We have normally we have an input coming. There are input coming, so we have a switch and to an inductor, to an output capacitor, and here you have a diode. Okay, so this is your input, this is your output, so you have ground. That's basically the DC-DC bulk converter. So this diagram, basically we also have this structure. If we follow the input from here, we have an input capacitor, then the input coming, and it goes through the first switching device, is the first MOSFET, basically the switch here, and then goes to the inductor, and go to the output cap, and the diode is replaced, so that replaced by another MOSFET, so it's a synchronized operation. So this basically is a diode here, and to the all the way to the ground. So that's basically the same topology. Okay, let's remove all the stuff here. So of course, I mean, you need to know, to control the DC-DC converter, you need to know the current inside the inductor. So you have a current sensing for the inductor current and during operation. And you have reverse blocking. That's kind of uses MOSFETs. That's you can disable this, turn off the MOSFETs when the part is disabled, so the output current will not go back to the source. Okay, and here we have one resistor here, and another configurable resistors to work with the resistor from the outside. This is basically your output coming here, goes through two resistors, the resistor divider, that's your feedback loop. You feedback the voltage, goes to the regulator, goes to the modulator, okay, to control the output or set the output. And here, this pass, here is the optional active discharge control. Okay, so when the parts, if you have this feature, when the parts is disabled, you enable this optional active discharge, so you can quickly connect the output voltage to the ground via a resistor, okay, to discharge the output. And we also have reference voltage for the internal use, and some undervoltage lockout control, thermal shutdown control, or like that. But the key topology is still like a typical DC-DC converter, but with two MOSFETs. Okay, and back to the data sheet. In the beginning, we talked about we have P MOSFET here, and another N MOSFET is two MOSFETs. There's a high side, we call this high side MOSFET, this is the low side MOSFET. Okay. So what's the benefits of the use a MOSFET to, because MOSFET also have a body diode, remember, like that. So the benefits with this use a MOSFET to replace this diode is just basically you can reduce the power loss. Okay, here the tables give you for the A version, you give you whole bunch of values if you want to output a certain voltage, and what's the resistance, feedback resistors should be. So you can just go to the table to check the value, to choose the proper resistors. And remember, in the meanwhile, when you choose these resistor values, you also set the threshold limit for the under voltage lockout. Okay, here's a bit things about how do you choose the inductor. The key things to remember, the inductor is based on the inductor peak current. You have to choose the proper inductor, right? So you choose based on the peaking current. And the input capacitors normally just typical ceramic capacitor, output capacitors, and just some X7R or X5R, very good temperature stability and very small DC biasing. It's up to a 22 microfarad is typical value. And here's when you enable the device, a bit tricky sometimes if you wire your enable pin to the input pins. Be careful because the enable your input has to be well established before you set the enable signals. Okay, so that means if your input voltage signals come very slowly wrap up, and even you cross the threshold voltage for the enables, but you might still not, the part might still not able to start because you're still wrapping up the input. So what you can do is use the RC circuitry to delay the enable signals. Okay, so the input signal is slowly wrapping up here, but the RC circuitry also slowly charge up. You slowly also charge up this capacitor with a resistor, so the enable signal also has been delayed. So that means when the enable voltage cross the threshold, your input voltage will be well established, so you can guarantee the part will start. So there's also a diode in here. I'm not 100% sure. I think it might be when you disable the parts. So when you disable, you cut the input signals, and these capacitors still have charged solid enable pins. If you have a diode here, you can quickly discharge this capacitor to disable the part. PCB layout routing, that's not much to talk about because it's a very simple device. And okay, this is the part numbers. When you order the parts, this is like a matrix, and it's so complicated in a way. So you need to choose the A part or B part. Okay, so the A part is configurable output, and the B part fixed output. Okay, and based on the family number 0, 1, 2, 3, that have a different output capacity, 350 milliamps, for example here, and also some parts even same output current capacity, some with active discharge, some with active discharge, some without active discharge. Okay, you need to be really careful when you choose these parts, and all the stuff here up to here is in this package. So if you choose the different parts and have a different package size, you have to go through the same exercise. Yeah, that's basically all for these parts. I think it's a very interesting little part, so maybe we could use it someday.